Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna. Hello, everyone. Good morning, good afternoon, good evening from me as well. I'm Guilherme Martinez Roura from the International Telecommunication Union, and I would like to welcome you all for joining today's AI for Good keynote, the future of robots for good, the quest for embodied artificial intelligence, the first AI for Good keynote of 2023. This session is part of the AI for Good robotics programming track, exploring how AI-powered robots are helping to unlock our human potential and advance the United Nations Sustainable Development Goals. We have a distinguished set of panelists today, but as always, we are counting on you, the participants, to help create a very interactive session. Without further ado, I would like to introduce our moderator today. Her name is Aleksandra Faust, and she's a senior staff research scientist and autonomous agents research lead at Google Brain. Sandra, welcome, and the show is all yours.
Thank you. Thank you, Leo, for the introduction, and hello, everyone. Thank you for coming. It is my great pleasure to introduce our speaker for today, which is Vincent Vanhoucke, who I've had great privilege to work with and learn a lot over the years. So Vincent Vanhoucke is a distinguished scientist and the senior director of robotics at Google. He co-founded and is the president of the executive committee on the Conference of the Robot Learning, which is now in its 6th year. His research has spanned many areas of artificial intelligence and machine learning, from speech recognition to deep learning, computer vision, and now robotics. And his lecture series on the Audacity has introduced more than 100,000 students to deep learning. He holds a doctorate from Stanford University and Diplôme d'ingénieur from École Centrale Paris. And without further ado, the floor is yours, Vincent.
Thank you for the introduction, Sandra, and welcome everyone. Delighted to have you all here. Let me share my presentation with all of you. So I want to talk about how Google has been really working, Google has been a pioneer in AI, and from the very first days has been trying to find new ways to apply AI to tackle the UN Sustainable Development Goals. I'm going to focus narrowly on one more speculative endeavor that we've been working on over the past few years, which is to attempt to tackle the problem of physical assistance. Google has been known to sort of help the world in their digital lives. And we've been asking ourselves the question, can we also consider tackling assistance in the physical world? Can we help people in their day-to-day perform physical activities? About 10% of the world's population today lives with a disability, and every one of us at some point or other in our lives have to tackle the problem of limited physical abilities, either because of illness or other factors. So we're asking ourselves, can we help? And can we help provide the kind of technologies that would really enable this kind of assistance to everyone in their daily environment? So I'm going to try and give an overview of some of the big technical challenges that underlie this this overall goal, and sort of walk through where we are and where we want to be in this journey to try and provide physical assistance to the world. The first challenge is the challenge for robots and for agents to navigate safely in human spaces. So the problem of the robot navigation in its simplest form is, please do not bump into anything. And if that's all that the challenge was about, that would be a relatively straightforward problem definition and something that we can tackle in more traditional ways using the traditional robotics techniques that are available today. And there is a lot of reasonable answers to those questions. But if you think of robots operating in human-centered environments, you have to really think about things at a high level. You have to moving things around, and so you have to navigate around them. You have a social presence around you. You have people who have some expectations of how agents in their environment should behave socially. And then you really would want to get to the level where you can collaborate with those agents and those robots. And the problem of interacting with humans and understanding human preference and desires and really navigating in a way that is compatible with those goals is an interesting higher level challenge. So we've been working on trying to give robots those kinds of capabilities by basically using forms of behavior prediction that enable the robot to interpret the pose of people, the gaze of people, where they're looking at and what they're doing, and understand how their position and trajectory may evolve over time and actually model those things. So if you have two people that are walking down a corridor and are talking to each other, you probably don't want your robot to sneak in between them and interrupt the conversation and get in the way. So you probably want the robot to take a longer detour, but preserve the social norms that everybody is accustomed to. So we've been evaluating all the issues around this. This is an example here on the left of a robot that would, simply be told, do not bump into things. On the right, you have a robot that has some notion of people around it and understands that this person is trying to walk past it and will pause way before the person is walking to give it enough room to walk around. Here's another example of a passageway that is, the robot wants to go through it and will obstruct it if it doesn't pay attention to what's going on. And on the right, an alternative way that is aware of what the humans in the scene are doing, and the robot will get out of the way, get out of the door, and let the people pass. And all those subtle interactions are really important to get right if we want to enable robots to live in human-centered environments, and are a really challenging problem to be tackling. So navigating safely in human spaces is one of the issues that we need to deal with. Another one is how to communicate with robots and how to instruct them in a natural way. And this has been one of our very strong focus over the last year. How do you teach robots to understand natural language? Natural language can be very unstructured, can be very vague, can be very context specific, right? Move this box a little bit to the left. What does a little bit mean? Left, what's the reference point? What's this box? It's not any box, it's that one. Arrange these books into a pile, put that over there. There is a lot of subtlety that's embedded in this kind of natural language that's completely natural to us, but to encode in something that a robot can understand is quite a challenge. So I'm going to talk about 3 different approaches that we've been taking to just give you an example of the span of things that you could consider as an approach to this problem. The first one is basically leveraging some of the recent advances in large language models. Those models have proven to be extremely competent at taking high-level descriptions of programs and at writing down the program that executes those high-level instructions. This power of turning language into a programming language suggests that we can basically leverage that for robotics. And we've been experimenting with this quite a bit. So the idea is you give the robot a natural language command, you let your large language model write a code that describes the policy that the robot should follow. Because what you're asking for depends on the context, depends on the visual recognition of what's in the environment of the robot. You need to be very deliberate about how you interpret those different commands. So you need to be able to detect objects. You need to have some primitives that enable you to do that. You need to basically understand what the concept of stacking here in this context means and be able to instruct the language model to produce code that corresponds to the concept of stacking. So it's a very rich area that enables, potentially everyone who is not a programmer to write robot programs. And if we can achieve that, then we've really lowered the bar, the accessibility bar for people to use robots. This is an example of the kind of things that you can do with this kinds of approach. Couple of examples of very natural language commands in a very limited scene environment. Place the blocks in the bowl with non-matching colors is an example here. That's a very high-level semantic question that the robot can turn into a program that it can execute and turn the high-level concept into something that's actionable for it. Another approach that you can take, which is very interesting, is the following. You can ask people to play with the robot and do anything they can think of, just perform random actions that are not necessarily directed, that don't really have a specific semantics. But then you can also ask people after the fact, when they watch the videos of you messing around with the robots, to describe it into words and describe what in natural language that action corresponded to. And now you have pairs of data, that's actions on one end and language on the other end. And you can train a model that will take the natural language actions and map it to the physical actions. And quite surprisingly, this works extremely well. So we've built a system that enables this kind of labeling of robot actions at scale, where people can enter natural language commands that correspond to the robots. And we can train a model that attends to this text and also takes into account the observation that the robot has and produce actions. So I won't go into the details of this model. It's quite complicated, but the important piece here is that you can really just use very data-driven approaches to accomplish this task. And this is an example of what you can get. This is a very simplified setup where you ask, push the green star between the yellow blocks, and the robot will, in real time, perform the action based on its understanding of the semantics of what it means to push something in between something else. Here's another example that I like. You can sort the blocks, or you can align them in a line or make a smiley face. Those are very high-level concepts, but by using a combination of this low-level control and planning and data-driven approaches, you can get the robot to, build a smiley face with the blocks, or align them, or sort them in corners. And this approach can be very, very powerful because it really leverages the data, and it can do such tasks in real time based on spoken commands that you would provide the robot. All right, I'll go over a third way of thinking about the problem. One thing that a language model can do, if you asked it in the right way, is how would you go about doing X, right? How would a robot do this thing step by step? I could, for example, ask a language model, how would a robot make me a coffee? And because the language model doesn't necessarily have a knowledge of what's around and what's available, it may say, well, it could go to the Starbucks next door and order a coffee. Or it could say, go to the kitchen and look for the coffee machine. Or it could assume that it's near to a coffee machine and say, press the button on the coffee machine. And all those options are, plausible from the perspective of a model, but the robot needs to know what it is capable of doing. And so we've been teaching the robots to have an understanding of what its own capabilities are. Can the robot actually drive to the next Starbucks? Well, probably not. But can he go to the kitchen if there is a kitchen nearby? Yep, maybe. And so we're going to be evaluating all the possibilities that the language model provides and tell the robot to execute on the one that is the most plausible. And if we do that in a loop, if you do that recursively, you end up with a plan that the robot can execute based on this natural language input. So this is what it looks like architecturally. If you go from left to right, you have, the language inputs. You give it, how would you put an apple on the table? You have a large language model that produces hypotheses about how would you do that. You would, find an apple, find a Coke. It could generate a lot of possible inputs. And then those inputs are going to be scored against this value function that the robot has, that understands what the robot thinks it's capable of given the context that it's in. And if you combine those scores together, then you end up with a plan that is both the right plan to execute on the action that you've asked for, and the right plan for the robots given the context that it's in. And this turns out to be a very effective way of controlling a robot. So here is a robot that is being asked, I spilled my Coke on the table. Would you throw it away? And the robot thinks about it, comes up with a plan, validates the plan against the different possibilities, and decides, okay, it's going to find the Coke can, pick up the Coke can, and then go to the trash can, and then throw it away, and almost put it in the trash can. And so this way of reasoning about long horizon plans using language models can be very scalable and very general, and really enables the robots to understand really ambiguous semantic requests. So we're very excited about this general direction. I think the notion that you can have general purpose robots that can be controlled using natural language is very new, and really leverages the most recent advances in AI in a way that is grounded and that enables really new capabilities that weren't possible before. All right, so we've talked about navigating safely in human spaces, and we have some plausible answers to this. We're starting to have some plausible answers to how do we instruct robots to perform tasks in a natural way. Now, the big challenge, and probably the one that is the most open at this time, is how do we do manipulation in the real world? And that's a thorny problem that has been one of the main subjects of inquiry in robotics for a long time. Manipulation in very controlled environments like factories or or when you can really control the environments well, is something that we've had plausible solutions to for a long time, but doing it in a completely unconstrained environment is really difficult. So we've been at it attacking this question for quite some time. This is an example of a setup that we put together a few years ago, where we had a collection of robots basically spending their days trying to simply pick up objects and grasp them, and doing attempts and logging whether they succeeded or not, to generate data to try and learn approaches and strategies for grasping and manipulating objects. And so we made a lot of progress. You can see on the left here was one baseline policy that we had. On the right was the new approach that we came up with. That's a lot more efficient. That's a lot faster and a lot more effective at picking up all sorts of objects and all sorts of diversities. So lots of progress in that direction. Just to give you a sense of the challenge, the robots have to be able to correct themselves when they make a mistake or they're unable. And this is something that we do without thinking on a regular basis, is to adapt our own behaviors to changing conditions if something is slippery or is not quite in the place that we thought it was. You have to deal with very challenging types of objects. Transparent objects are a thorny issue because a lot of cameras don't really register them well, and understanding how you handle them and how do you manipulate them in the right way is a very challenging thing in general. And then you have to understand the physics of objects. And that's another problem altogether. How do you infer the physics of any object based on your prior knowledge of, basically what a banana weighs and how you may be able to manipulate it in a way that is physically realistic. This is a robot that we put together a few years ago as well, that is basically simply attempting to toss objects and in a bin and adapt itself both where it's being where the bin is and to the shape and dynamics of the objects. The real world is really unforgiving in that respect, right? The level of diversity that we that exists in the real world is staggering, and the different strategies that you may think of in terms of manipulating and grasping objects can be extremely complex and difficult to manage. And so that's why data-driven approaches are really interesting in this context, because you can experience a lot of different configurations that you may not be able to program into your robots, and data-driven approaches really shine in that respect. The catch is you have to collect a lot of data, and so that's what we're doing. This is an example of a number of tasks that we've been collecting data on with our robots, grasping all sorts of objects in all sorts of conditions, and attempting to perform a variety of tasks. The approach is to give you a little bit of a flavor for what things look like from and how we think about those kinds of manipulation problems. We basically need to learn models that take as an input an instruction what the robot is supposed to do, take as an input a series of images, and then output actions that are the manipulation and grasping actions. And what we put in the middle of that is a relatively complex neural network that runs continuously. This one runs at 3 Hertz, so one action every third of a second. And that adapts itself based on the visual inputs that the system observes, and adapts its actions based on the outcomes that it observes. This model has been is our state of the art today, and it enables us to really explore the space of what is possible with the data that we have. So, obviously we have this hypothesis that more data is better and will enable us to generalize better and get better performance. And this is what we observe. If we increase the amount of data, the performance of our system works better. One interesting tidbit that we found out throughout this research has been that if you reduce the data diversity without really changing the amount of data that you have, by just focusing on removing the data that's the least, that adds the most diversity to your system, the performance drops very, very quickly. And so the insight here has been that really data diversity, when you're trying to train a model for manipulation, is really, really important. And it may not be as much a matter of how much data you collect, but really it's about how diverse the data is. And that insight really ends up changing the way we think about the problem and potentially opens up new avenues to be a lot more data efficient and improve the performance of systems by really trying to think of ways that we can improve the diversity of the data collection that we're performing. So we're excited about those directions. We won't claim that we have entirely solved the problems by any stretch, but we have new answers and new ways to approach those questions that are very exciting in general. So, like I said, we're really at the beginning of this journey. I mean, there's a lot more things that we need to understand and to develop for us to really be able to build robots that will seamlessly integrate in the human world. But when we do, I really hope that the physical assistance will help enable more freedom, more independence for people who have, for instance, limited physical abilities, people with disabilities, the elderly, and being able to augment one's physical activity just by instructing robots to help could really be transformative for a lot of people. And I'm hoping we can, really, really make new strides in this journey and really bring robots to places where they can be the most helpful for people. So I will stop here, and I will be delighted to take any questions from the audience and from our moderators. Thank you.
Thanks so much, Vincent. We do have several questions from the audience, so let's start there. Chris Zielinski would like to know, what is your view of the anthropomorphic robots made to look like living creatures?
If you want to live, if you want your robot to operate in a human world that has been designed for humans, it's very natural to think of the robot having a human form, not because you want necessarily to make that robot a pretend human for any other reason that the world around us is designed for people. So it makes a lot of sense that if you, by default, start with a form factor that looks like a human, it will have the same level of access to, be able to climb upstairs, open doors, open drawers, manipulate human design objects, designed for humans. The problem with from the perspective of a researcher and from the perspective of bringing those robots to commercial success is that the human form factor is extremely complex, right? We have a lot of degrees of freedom, and building a robot that is as complex as a human from a dynamics and kinematics perspective is really expensive. The robot can be pretty brittle. The power density, the strength that you need to have is all the engineering requirements that are needed to make this robot practical and commercially practical are really daunting. And so it's tempting to simplify, right? It's tempting to try and find form factors for robots that are, slightly simpler than the form factor, like there is a fully humanoid, but still has the same affordances, the same capabilities, or similar enough capabilities that you can make the whole system commercially viable. It's an interesting dilemma for robotics in general, because there is this tendency to wanting to build a robot that is universal and that can do everything a human can do. And then if you look at what's worked in the marketplace, you have robots in your home. They're called the washing machine and the dishwasher, and they look nothing like a human. And so that tension is not going away. And the economics, I think, of robotics are going to dictate what ends up working in the marketplace.
But I think the question here was more focused on not humanoid robots necessarily, but more robots that look like humans, like Sophia or...
Oh, there's an interesting question there about robot as a tool versus robot as an agent, right? And we've been talking about robots that can understand natural language, and so it would be very tempting to try to really anthropomorphize robots and make robots that look similar to humans, and that also gets into all the issues of the uncanny valley and being able to sort of relate to robots that are very close in terms of their behaviors and aspects to humans. I like the notion. I like the perspective of robot as a tool personally better, even if you interact with it in a human using human natural language, because I do like the notion of keeping people at the center and designing the technology around people in the service of helping people accomplish tasks. I think we shouldn't lose sight of this goal. And until we get to the point where the robots can be actually useful to individuals, I think we have a lot of work to do just on the capabilities that a robot can have, irrespective of its form factor. And that's really the key scientific problem that I think is worth solving here.
Thanks. I have a question from Anne Bush, who would like to know, what impact do you believe robots will have on the healthcare in the next 5 years?
In the next 5 years, 5 years is not a long time by the standards of the kind of research that we do.
How about 5 and 10 years?
5 and 10 years. We're seeing a lot of robots impacting healthcare delivery today by simply helping transport goods in healthcare facilities, for example. And I think that's as a first step towards robots being useful is a very good one, because there's a lot of sort of toil in workplaces that is just about taking something from point A to point B. And it's not a good use of people's time to just be doing the moving things from point A to point B. So I think that's where most of the impact is going to be in the near term. Longer term, there is a lot of people who would love to find ways of having robots help with physical tasks that relate to healthcare facilities involving patients, right? Enabling, helping patients' mobility and things like this. I think there is a good chance at robots impacting access to things. So being able to instruct a robot to bring something to a patient or to help them manipulate objects around them. The next level over would be to have robots that help actually physically manipulate patients in healthcare facilities, like help them stand or help them shower or things like this. Anything that involves actually touching humans and manipulating humans in some way is a much more difficult problem to tackle, because the safety concerns there are paramount and are kind of trump the everything else in the equation. I'm more pessimistic about that having changing materially in the last 5 years, but who knows? The field is really evolving really quickly today, and it's I don't really I've not been very good at my own predictions in the past, and so I don't really trust them.
I don't think anyone is nowadays. As you're outlining the vision of robots getting into homes, hospital care, getting really personal, what are your thoughts around cultural differences and personal preferences? And Marcus Beck had a question about what would be the most important point for you in terms of digital ethics in the context of robotics for good.
The issue of personal preferences and how do you manage them is really front and center as soon as you have robots really interacting with people. We see that a lot, even in the, I was talking a lot about social navigation. Even if you have a robot that doesn't interact deeply with a person, just the fact that a robot is in a human-centered environment already poses a lot of questions about human preferences. It can simply be about, if you're in a corridor and there's a robot, do you pass the robot on the right or on the left? That is something we don't necessarily think about, but some societies pass on the right, some societies pass on the left. It tends to depend on where your cars drive on the road, and if it's left or on the right. And those preferences are kind of subtle, but are the difference between the robot being seamless in your environment or the robot being extremely annoying and interruptive. And so human preference is at the core of a lot of the things that really are key to making them actually work in the real world. You probably will want something very different from a robot if it's living in your living room compared to if it's living in an office environment where there is more of an expectation of other agents evolving in this environment and owning some part of the floor space, as opposed to your home is your home. And I would suspect that if the robot was interruptive in this environment, it would get annoying very quickly. So one of the things that I have really high hopes for in this context is that programming human preference is really hard, and that means that would imply we actually fully understand human preferences, and I don't think we do. And human preferences change and are very contextual. That's why machine learning is an interesting paradigm to really sort of develop a mental model for human preferences, because you basically are deriving those human preferences from data. And data really implicitly tells you what those preferences are. And if you can take that data, these observational data from actual humans in actual environments, and turn that into something that can be learned, then you have a shot at really sort of have robots that really encode human preference and are respectful of them. So I'm very hopeful about this general direction.
Can you comment on the ethics implications and potential implications on the labor force? As you mentioned, I mean, we talked about the healthcare, that means physical therapists, nurses, and
yeah, there is a lot of there's a lot of implications for ethics, right? So any technology that that enables people to do more, that do better, faster, can be used either in a way that either enhances people's lives or affect their livelihood in a negative way, right? And we can't entirely control that at the time of technology development, right? And it really depends on the ways it's been applied. What we can do, however, is focus on the kind of technologies that keep people in charge. And I think that's the key for us, right? So again, taking the example of social navigation, if your robot navigates in a way that is not social, that means you have to make a hard decision about, either you have robots or you have people, but you can't have both, right? And if you decide that, if someone decides that the economics are such that having robots is better than people, then robots will take over the environment and humans will be excluded from it. If you make robots social, then you can actually have coexistence of humans and robot and make a workplace or an environment that is more friendly to people and gives you a lot of ways for humans to be involved in the process. Language is another example where it is really all about keeping humans involved in what we're developing, right? So you can put a language-enabled robot in front of anyone, and people can interact with it and derive value from it. And that's irrespective of their technical skills. I think that's really important because right now, to operate robots, you need a certain level of technical skills and you need a certain level of training and competency that might not be evenly distributed. If we can really make that completely seamless, that really opens up the accessibility and the opportunities for everybody to be using robots in their environment. And I'm really hopeful that we can really sort of add value and really sort of improve the situation for a broader range of people.
Thank you. I want to be mindful of time. I know we had a delayed start and we're at the hour now. There are a couple more questions. Do you have time or should we?
Perfectly fine by me.
Okay. So there is a question from John Cassaden. Is it reasonable to see robots being affordable to the masses? Will they be owned, rented, or provide social services?
Yeah, the economics of robotics are brutal, right? Robots are very expensive, and the complexity that underlies, anything that has to do with complex actuation can be very difficult and dominate really the equation. It's interesting though that if you look at the past 10 years, the trends have been. Robots are getting very, very cheap compared to where they were. They're still expensive, but the rate of progress in terms of making them affordable is remarkable. You can get a very, very good robot arm today under $10,000, which was completely unheard of even 5 or 7 years ago. So there's a lot of progress on making the economics of robotics a lot better. I suspect it's still going to be a thorny issue in terms of enabling broad access to robots, because at the end of the day, until there is a much broader mass market adoption of those technologies, we will not see the economies of scale quite yet. The total number of installed robots in the world is shockingly small compared to what people may expect, and they haven't really reached the kind of economies of scale that we see from cars and other sort of consumer goods.
There are a couple of technical questions. Dennis asks, I'm really not knowledgeable about AI yet, but do you think that image analysis and YouTube videos can be used to help robots learn skills?
Yes, it's a very interesting question. There's a lot of people who are attempting to do this right now. I won't say that that the answer is entirely yes yet. However, one thing that's been interesting in recent years is that we've been seeing the rise in those very large foundation models that are really derived from all the sources of text and visual data on the internet. And those models are not trained specifically for robots, right? They tend to be more about, mapping natural language to images or images to natural language and things like that. So multimodal models, but not necessarily geared towards robotics. And we increasingly find that those models are actually very, very useful for situational awareness. Like they're good enough that you can use them to really interpret the world around you and sort of provide a foundation for the robot to reason about its environment. So indirectly, you essentially are taking data that is available in other modalities like videos, like images on the web, and turning them into something that is useful for robots. Learning directly skills from videos, from examples of people doing things on YouTube is one area of research that's extremely active right now, and that a lot of people are trying to make work. But I don't think we can credibly say that it's working yet, or that there's hopeful signs, but nothing that I would say is proof that this is the right path yet.
So I have two more questions. One is from Jairam that says, can you discuss about annotation challenges for manipulation? Also talk a bit about a generic approach for self-learning versus human annotation.
Annotation challenges for manipulation, yes. So one of the big problems that we have in robotics is what we would call success detection. When do we know that the robot has actually done the thing that we asked it to do? If you're a person, it may be obvious to you that the task has succeeded. If you're trying to automate this process for the purpose of annotating data, for example, just figuring out if the task has been completed can be difficult. Like if an object is really in the gripper of the robot, or if nothing has fallen over while you were manipulating things. So it's one of the very difficult problems in terms of scaling data collection is this annotation problem. How do you do that in a way that is inexpensive enough and reliable enough, and respects the semantics that are sometimes subtle of what you ask the robot to do. Very challenging problem. We right now do a lot of human data collection for that reason, because this provides very high quality data. It's not cheap, but it really seems to scale relatively well and be a good path forward. If we could do data collection in a way that's more automated. Obviously, there's a lot of work right now going on that tries to tackle this as an online learning problem, where you deploy robots in an environment and you iteratively online learn and improve its skills. And for that, you need to be able to do self-annotation, if you will, and that's a very challenging problem.
And the last question for today, Mark Sutton is asking, recently we have seen some discussion about large language models taking shortcuts and autonomously building real-world models. Won't AI robots with real-world interfaces accelerate that process? And if so, shouldn't we be careful about AI becoming a black box?
Yes, it's a very good question. I'm actually hopeful for exactly the opposite. I am hopeful for robotics and to help ground large language models in reality and provide factuality to them. The problem that large language models have today, and I don't think it's a fundamental problem, I think it's mostly a byproduct of how the way they're constructed today, is all their data and so all their knowledge comes from just web sources. And there is really nothing that connects them to the real world besides that data. And it in particular doesn't connect with your own reality. It only connects with, it's something very general. Like it understands that a cup is a cup, but your cup it's a different cup. It's got very specific properties, and a model that just reasons in generalities will either be underpowered or potentially make things up because it doesn't know the particulars of your situation. My hope is that by connecting those large language models with the real world through robots, through agents, we can actually provide the kind of grounding that it's missing and help with issues of context awareness, factuality, understanding of physics, and more generally sort of understanding of your own world as it is today, as opposed to this simulacrum of a world that exists on the web.
Yeah. Well, thank you. That's all the questions. And Vincent, I want to thank you for the time and for sharing your thoughts, and to the audience for asking really great questions, and for the organizers for having us here and organizing everything. Thank you.
Thank you so much. Really appreciate it.
So thank you very much, Sandra. And a big thanks to our keynote speaker, Vincent, as well to all the participants for making it such an interesting discussion. And now we encourage you to check out the AI Food program online to see more robotic sessions that may be of interest to you. And now it's the end of this section and the start of the networking in the AI Food neural network with maybe the panelists and participants for the next 10 minutes. So see you all in a couple of minutes, and I will give the floor back to Anna for the closing information. Thank you very much.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good. you.